Hi all. So we are continuing with our class EC303 Applied Electromagnetic Theory. So we have been looking at module number 4, transmission lines. In this lecture we are going to look at a parameter called as standing wave ratio. Also, we are going to see the average power at any point on the transmission line. Okay, and we are trying to derive this in terms of for the lossless transmission line. So let's first see the standing wave ratio. Or SWR or voltage standing wave ratio VSWR, and it is either denoted by S or rho. So we will use S as our notation. The standing wave ratio S is defined as the magnitude of maximum voltage by minimum voltage, or is equal to the maximum current by minimum current in transmission line, or you can say at any point. So we will consider a lossless transmission line where the attenuation constant alpha is equal to 0. So your propagation constant gamma is equal to alpha plus j beta, that is equal to j beta. Okay. We have seen the expression for the reflection coefficient tau of Z as V0 minus by V0 plus e raised to 2 gamma L. So for lossless transmission line, this will become, you substitute gamma with j beta. So the value of gamma will become j beta. So tau of Z is equal to V0 minus by V0 plus e raised to 2 j beta. Similarly, we have also derived the expression for reflection coefficient tau of Z at Z equal to L minus L dash, or at a distance L dash from the load. So this was tau L e raised to minus 2 gamma L dash, which for lossless transmission line will become tau L e raised to minus 2 j beta L dash. Okay. Because we are going to consider lossless transmission line, it is easy to derive, and we will stick with the basic things. Fine. We know the expression for Vs of Z for a lossless transmission line as V0 plus e raised to minus j beta Z plus V0 minus e raised to plus j beta Z. Now, as we have said earlier, in the transmission line with characteristic impedance Z0 and load impedance ZL, let us consider a point at a distance L dash from the load. So this is at a distance L dash from the load, and your generator is connected at Z equal to 0, load is at Z equal to L. So the distance between generator and the point is L minus L dash. Okay. So, Vs at Z equal to L minus L dash is equal to V0 plus e raised to minus j beta. So, wherever there is Z, you substitute by L minus L dash plus V0 minus e raised to j of beta into L minus L dash. Okay. So, I can take V0 plus e raised to minus j beta L minus L dash common. So, this will become V0 plus e raised to minus j beta into L minus L dash, or let me write in as a complete sentence. So, I can write Vs at Z equal to L minus L dash is equal to V0 plus e raised to minus j beta of L minus L dash multiplied by 1 plus V0 minus e raised to plus j beta into L minus L dash divided by V0 plus e raised to minus j beta into L minus L dash. Okay. Because I just took V0 plus e raised to minus j beta L minus L dash common out. So, there will be 1 here and it will come in denominator here. Fine. So, I can write Vs of Z equal to L minus L dash is equal to V0 plus e raised to minus j beta into L minus L dash multiplied by 1 plus. So, if you look at this term, okay, we have already proved in the last class that you can express the reflection coefficient in terms of the reflection coefficient of the load multiplied by some exponential term. So, this is actually a reflection coefficient at any point L dash from the load. So, I can write this is actually the reflection coefficient at a distance L dash from load. So, we have already seen that expression. Okay. We have already seen that that is equal to this one. Okay. So, I can substitute this as 1 plus tau L e raised to minus j 2j beta L dash. Okay. Now, this is Vs at any point L dash from the load. So, we want to find V max or the magnitude of the maximum voltage. That is what we want to find at any point L dash. So, I can write V max is equal to, or the magnitude of V max is the magnitude of Vs at Z equal to L minus L dash maximum, that is equal to the maximum value of the modulus of e raised to minus j beta L minus L dash multiplied by 1 plus tau L e raised to minus 2j beta L dash, the maximum value of this. Okay. So, we want to find the maximum value of this quantity. Okay. So, let me review some of our complex identities. So, this, because we have e raised to j term, which means it is a complex quantity. So, you know that if Z1 and Z2 are complex numbers implies the magnitude of product of the complex numbers is equal to the magnitude of first number multiplied by the magnitude of second number. So, if Z1 is equal to A plus JB and Z2 is equal to C plus JD, so I can write the magnitude of Z1 as root over A square plus B square and magnitude of Z2 as root over C square plus D square. Okay. So, this is one identity that we are going to use. So, if you look at this whole term, okay, so this is first complex number and this is the second complex number. Okay. So, I can write this as Z1 and this as Z2. So, V max is equal to magnitude of e raised to minus j beta of L minus L dash multiplied the magnitude of 1 plus tau L e raised to minus 2 j beta L dash. Okay. Fine. Now, again, if you consider this quantity, so this can be considered as Z1 and this can be considered as Z2, right. So, I can write again as this is equal to magnitude of V0 plus multiplied by magnitude of e raised to j beta into L minus L dash multiplied by the magnitude of 1 plus tau L e raised to minus 2 j beta L dash. So, V0 plus we do not know what is the actual quantity. So, that will be remaining as it is. So, what is this term? Let us expand. E raised to minus j beta into L minus L dash is actually cos of beta L minus L dash plus j sin of beta, sorry, it is not plus, it is minus, because it is a minus j, sin of j, sorry, sin of beta L minus L dash. And the magnitude of e raised to minus j beta of L minus L dash is basically, so this is there is a j here. So, this is basically square root of cos square beta L minus L dash plus sin square beta L minus L dash. So, this is root over cos square theta plus sin square theta, which is equal to 1. Okay. So, I can write mod V max as mod V0 plus or magnitude of V0 plus multiplied by 1 multiplied by 1 plus tau L e raised to minus 2 j beta L dash. Okay. Now, we need to find what is the maximum value of this. For that, tau L is equal to ZL minus Z0 by ZL plus Z0 implies tau L is complex because impedances are complex. ZL is complex, Z0 is also complex. So, any combination of complex numbers will give you a complex number. Okay. Fine. So, we have to find the maximum value of 1 added with the product of two complex numbers. So, for doing that, again we will review one concept. So, if Z1 is equal to A plus JB implies I can represent Z1 as the magnitude of Z1 multiplied by e raised to j phi, where phi is tan inverse imaginary part which is B by the real part which is A. Okay. So, the B is the imaginary term and A is the real term. Okay. Fine. If you want to have an example, let us look at an example to make it clear. Let us say Z1 is equal to 3 plus 4j. So, the magnitude of Z1 is equal to root over 3 square plus 4 square, that is root over 25, that is equal to 5. And phi is equal to tan inverse 4 by 3, that is 0.927 radian. So, I can represent Z1 is equal to 5 into e raised to j 0.927. So, if I expand this, this is 5 into cos 0.927 plus j sin 0.927. Now, cos 0.927 is 0.6 and sin 0.927, which is in radians, is 0.8. So, if you multiply, this is 5 multiplied by 0.6 plus j 5 multiplied by 0.8. This is 3 plus 4j, which gives you the result we have started with. Okay. Fine. So, tau L is complex. So, I can represent tau L as the magnitude of tau L multiplied by e raised to j phi. Okay. Because since tau L is complex, the phi is actually tan inverse of imaginary part of tau L by real part of tau L. Okay. So, I can write now mod V max is equal to mod V0 plus, or I say mod as magnitude, multiplied by 1 plus mod tau L, or I can say magnitude of 1 plus magnitude of tau L e raised to j phi into e raised to minus 2j beta L dash. Okay. So, you can combine these two. So, I can write this as mod or magnitude of V0 plus magnitude of 1 plus tau magnitude of tau L e raised to j into phi minus 2 beta L dash. Okay. So, we know modulus of tau L, this is positive. Okay. So, what happens to this term? So, the maximum value of the whole V max depends on the maximum value of this term. Okay. So, e raised to j phi minus 2 beta L dash has the maximum value plus 1, because this is sin phi minus 2 beta L dash plus j, sorry, cos phi minus 2 beta L dash plus j sin phi minus beta L dash. So, this is maximum is 1, because this is cos of phi minus 2 beta L dash plus j sin of phi minus 2 beta L dash. So, the maximum real value is 1. So, this has max real value is equal to 1, because we are taking the magnitude, we are not considering the complex part. Okay. So, I can say the maximum value, magnitude of maximum voltage is mod V0 plus into the magnitude of 1 plus mod tau L. Okay. So, we can make this as a bracket, because the terms inside is positive and real. Okay. So, the maximum value of the voltage at any point on the load is the product of the magnitude of V0 plus and 1 plus the magnitude of reflection coefficient. So, this is the maximum value in the transmission line. Maximum voltage value in transmission line. So, can we find the minimum voltage value? If you go through the same procedure, you see V min has a similar expression, where you have V0 plus magnitude 1 plus mod tau L e raised to j phi minus 2 beta L dash. Okay. So, the minimum value will also depend on this. So, what is the minimum value of this? And we know the minimum value is minus 1. So, e raised to j phi minus 2 beta L dash min is at minus 1. So, we can say mod V min is equal to mod V0 plus into 1 minus mod tau L. So, this is the minimum value. So, now we can define our SWR, or standing wave ratio, denoted as S, is equal to magnitude of maximum voltage by the magnitude of minimum voltage. So, that is equal to V0 plus into 1 plus mod tau L divided by V0 minus magnitude multiplied by 1 minus mod tau L. So, V0 plus and V0 minus will get cancelled, and you will end up having the standing wave ratio is equal to 1 plus mod tau L by 1 minus mod tau L. So, that is the expression for standing wave ratio. Okay. So, you can look upon what is the maximum value of standing wave ratio, what is the minimum value of standing wave ratio, and what happens at these values. What happens to reflection at maximum and minimum values of standing wave ratio. So, you can look at it yourself what this is. We will explain this in the class. Okay. So, this is the standing wave ratio. Now, we also told that the standing wave ratio can be written in terms of the current coefficient, current max. So, this is I max by I mean its magnitude. Okay. So, you will end up having the same expression. Okay. The derivation is exactly same. So, you can have as a homework, derive the standing wave ratio S starting from expressions, or I would say expression of IS of Z. Okay. Fine. Now, we can represent the maximum impedance in terms of VSWR. The maximum impedance Z max. So, Z is actually the ratio of voltage and current. So, if you want to have maximum impedance, you should have maximum voltage and minimum current. So, if current is minimum, this value will be maximum. If V max is maximum, this also will be maximum. So, I can write this as V max divided by, or I would say the magnitude. V min, I min will happen when there is a V min divided by Z0. We also told that the voltage and current are related by the characteristic impedance. So, the I min is equal to V min by Z0, but we also know that V max by V min is actually the VSWR. So, I can write this as Z0 into S. Similarly, minimum impedance happens at minimum voltage and maximum current. So, this I can say as V min by V max by Z0. So, this is again 1 by S, because this is the inverse of S or inverse of standing wave ratio. So, I can write this as Z0 by S. So, these are two important relations where you say the maximum impedance is related to the characteristic impedance and VSWR or SWR. Similarly, the minimum impedance is also related to characteristic impedance and VSWR. Okay. Fine. So, that completes our discussion on standing wave ratio. Now, let us look at the average power at a distance L dash from the load. So, we are making a small change in our representation of axis in this case, so that the derivation is easy. So, till now what we have considered is you have a generator, you have a transmission line, you have a load, okay, and you say that this is at Z equal to 0 and the load is at Z equal to L. Okay. and your reflection coefficient at the load tau L is equal to V0 minus by V0 plus e raised to 2 j, or let me make it more specific. Let me say this is a general thing. So, this is 2 gamma L. So, this is what is reflection coefficient at load. Okay. Now, to derive the power, we are making a change that we are just shifting the axis. Okay. So, we already told that everything is related to the load. So, from the load, how much is the distance? That is what matters. So, we can shift the axis in such a way that this is z equal to L or z equal to 0, and if you travel backwards, so this is z equal to minus L, because the direction, actual direction is this way, positive direction. So, this is positive direction, the backward will be negative direction. So, we will have z equal to minus L. So, it does not matter at when you shift the axis, it will not change any expressions for input impedance or the value of characteristic impedance, nothing will change. So, this is for our convenience, so that the derivation can be done easily. Okay. So, this change in axis will not change Z in or Z0. Okay. This is only purely for our derivation. Fine. So, now let us see what is tau L. This is V0 minus by V0 plus e raised to 2 gamma. Previously, we have seen that when Z equal to L, you have a L term here. Now, Z equal to 0 at the load. So, this is multiplied by 0. So, that is V0 minus by V0 plus. So, that is now your new tau L. Okay. So, that we will use in our equation. Now, you define the average power as 1 by 2 into real part of Vs of Z multiplied by Is conjugate of Z. Okay. So, let us consider a point L dash from the load, which means Z is at minus L dash, and we are going to consider the average power at this point. Okay. So, what will be the value of Vs of Z? So, Vs of Z, our general expression is V0 plus e raised to minus gamma Z plus V0 minus e raised to plus gamma Z. Now, the point is at Z equal to minus L dash. So, I have Vs of at Z equal to minus L dash is equal to V0 plus e raised to plus gamma L dash plus V0 minus e raised to minus gamma L dash, because you are substituting Z equal to minus L dash. Fine. Okay. So, to make it bit more simpler, let us consider a lossless transmission line. Okay. Similarly, I can have my Is of Z equal to minus L dash as V0 plus by Z0 e raised to gamma L dash minus V0 minus by Z0 e raised to minus gamma L dash. Okay. So, let us consider lossless transmission line. So, our Vs of Z equal to minus L dash is equal to V0 plus e raised to j beta L dash plus V0 minus e raised to minus j beta L dash. Okay. And considering for I0, Is, you see there is a conjugate at the top. So, what is Is conjugate of Z equal to minus L dash? That means, this will become V0 plus conjugate by Z0 e raised to, now when you conjugate, or let me write without conjugate so that you will understand. So, this is V0 plus by Z0 e raised to j beta L dash minus V0 minus by Z0 e raised to minus j beta L dash. So, Is of Z equal to minus L dash conjugate is equal to V0 plus by Z0 conjugate. So, when you conjugate e raised to j beta L dash, it will be e raised to minus j beta L dash minus V0 minus by Z0 e raised to plus j beta L dash. Okay. Now, let us multiply both, because that is what the equation says. So, I will just say Vs of Z multiplied by Is conjugate of Z, this is equal to, so we will substitute this equation and this equation. So, this is equal to V0 plus e raised to j beta L dash plus V0 minus e raised to minus j beta L dash multiplied by V0 plus conjugate by Z0 e raised to minus j beta L dash minus V0 minus by Z0 conjugate, sorry, there should be a conjugate here, multiplied by e raised to plus j beta L dash. Okay. Now, let us multiply each term, or let us make it more simpler. Let us take V0 plus outside from here and V0 plus conjugate by Z0 out from here. So, this will be equal to V0 plus multiplied by e raised to j beta L dash plus V0 minus by V0 plus e raised to minus j beta L dash multiplied by V0 plus conjugate by Z0 e raised to minus j beta L dash minus V0 minus conjugate by V0 plus conjugate e raised to j beta L dash. When you take V0 plus by V0 plus conjugate by Z0 outside from here, Z0 will get cancelled. So, we will get the ratio of V0 minus conjugate and V0 plus conjugate. But we have seen that V0 minus by V0 plus is equal to tau L, that is from this equation. Okay. So, I can substitute that and say Vs of Z into Is conjugate of Z is equal to V0 plus into e raised to j beta L dash plus tau L e raised to minus j beta L dash multiplied by V0 plus conjugate by Z0 into e raised to minus j beta L dash minus tau L conjugate e raised to j beta L dash. Okay. Let us cross multiply. When you multiply V0 plus and V0 plus conjugate by Z0, it will be mod square of V0 plus. Z1 conjugate Z2, Z1 conjugate Z1 is mod Z1 square by Z0. Okay. Now, if you multiply e raised to j beta L dash into e raised to minus j beta L dash, you will get 1. So, this will be 1. Now, if you multiply e raised to j beta L dash and minus tau L conjugate e raised to j beta L dash, you will get minus tau L e raised to 2j beta L dash. Okay. So, this will give you this. So, this multiplied by this, and this multiplied by this gives you 1. Fine. Now, if you multiply tau L e raised to minus j beta L dash and this, so you will get, so there is a tau L conjugate here, you will get plus tau L e raised to minus 2 j beta L dash. And at the last, if you multiply these two, you will get minus mod tau L square, because you have e raised to minus j beta L dash into e raised to plus j beta L dash, which become 1. There is tau L into tau L conjugate, which is mod tau L square. Okay. So, actually tau L e raised to minus 2 j beta L dash whole conjugate is equal to tau L conjugate e raised to 2 j beta L dash, which is these two. So, if Z1 is equal to A plus JB, Z1 conjugate is equal to A minus JB, and if you subtract Z1 conjugate from Z1, so you will get A minus JB minus A minus JB. So, that will be minus 2 JB, implies this is purely imaginary. Okay, fine. So, make note of that result. Okay. So, our power P average is equal to the real part of Vs of Z multiplied by Is conjugate of Z. So, this is equal to real part of mod V0 plus square, I think there is a square missing, square by Z0 multiplied by 1 minus tau L conjugate e raised to 2 j beta L dash plus tau L e raised to minus 2 j beta L dash minus mod tau L square. Now, if you look at each term, this is real, this combination is imaginary, which we found from here, and this is also real because it is the square of magnitude, which is always real. So, this term, when you take the real part, this term will disappear. So, you will get, so sorry, there is a 1 by 2 also missing. So, the average power is 1 by 2 magnitude of V 0 plus square by Z 0 multiplied by 1 minus mod tau L square. So, that gives you the average power at any distance L from the load. So, this gives you average power at a distance L dash from load. Okay. So, you can find out what happens when tau L equal to 0, tau L is equal to plus 1 and tau L is equal to minus 1. So, you can explain what happens. Okay. So, when you see tau L equal to, when you put tau L equal to 0 in this equation, what happens to the average power? When you put tau L is equal to plus 1 or tau L is equal to minus 1, what happens to the average power? Okay. So, that concludes our session today. So, we have looked at the standing wave ratio and average power, and we found the expressions for both. So, this completes module number 4 for the course Applied Electromagnetic Theory, and thank you for listening.